This is the P5 electricity in the home topic. Much of this builds on what you did in P4 and in P1 as well, so it brings together lots of different things, but all of those topics are going to be on paper 1 of your GCSE, so therefore they might ask you questions that bring together like different ideas about energy and about electricity all together in the context of electricity in the home. So let's start off with talking about two main things. So alternating current, or AC, and then direct current, known as DC. So you need to know the difference between these two. So alternating current, as the name suggests, changes direction. So we have positive and negative. So it cycles constantly between, between the positive and the negative direction. Okay, so the number of cycles per second, so it's 50 hertz, so that's 50 cycles per second, remembering that frequency is equal to 1 over the time period. So that's an equation that you need to know. An alternating current is what is used in mains electricity. So mains electricity being anything that you kind of plug into a socket is what we would refer to as mains, and you need to know that it is 230 volts. They will expect you to use 230 volts in a calculation without reminding you that it's 230 volts. So they might say whatever has is connected, like it runs on mains electricity, it has a current of, I don't know, 5.7 amps. What is the resistance? And so you would be expected to use R equals V over I and recall that V would be 230. So try and get into the habit of whenever it says mains electricity in a question, underline or highlight it, whatever your strategy is for picking out key terms, and just try and get into the habit of annotating next to it 230 volts every single time, so that you're reminding yourself that that's what the value of mains PD is in the UK. So direct current, as the name suggests, if we have positive and negative, just goes in one direction, so it stays at one value for the whole time in one direction. And an example, whoops, that didn't work. An example of this would be like a battery uses direct current, so goes in one direction. So if it was a 3-volt battery, this would be 3 volts. So you need to be able to like read that off a graph as well. Okay, so let's focus on mains for a moment. So you need to be able to know what happens with a plug. Okay, so I'm going to very quickly draw a plug. So you would have the main cable going into the plug. You have something here called the fuse. Okay, and the wire that is attached to the fuse is the live wire. Okay, so the live wire is attached to the fuse. There is a wire that goes up to the top pin, and that is called the earth. And then there is a wire that goes to this bottom pin here, and that is called the neutral. You need to know the colours of these. So neutral wire is blue, the earth wire is the green and yellow striped, and the live wire is brown. One of the most common errors that comes up in this question, which is quite a simple question like labelling a plug and giving the colours of the wires, and often you'll only get 1 mark for getting all 3 of them, is that people for some reason have it in their heads that the live wire is red. It's been brown for decades, so it's definitely not red in a British plug. So you do need to learn that it's a brown wire, because they'll often put red in as a bit of a distractor to trick you. Well, not to trick you, but to check that you actually know what it is you're talking about. So think about it like this. The live wire, so the circuit actually runs through the live wire and the fuse, and then the circuit is made through the neutral. Okay, so as long as nothing goes wrong, the earth wire doesn't have a current in it. Okay, so the potential difference is between the pin with the live wire and the pin with the neutral. Okay, the earth wire exists in case one of the other wires touches, or something inside the appliance touches the outside of the appliance, which would ordinarily make the appliance live. But the earth wire grounds it, so would take that electricity to ground, which then makes it safe. So the earth wire is a safety kind of mechanism. A fuse is a safety mechanism as well, and I'll come on to that in a second. So some plugs are, or cables are 2-core. Okay, and what that means is that they only have the live and the neutral. So there is no earth wire. And it tends to be, so it would need to have plastic casing and what's called double insulation. If it had metal casing, it has to be a 3-core plug or 3-core cable that goes to a plug with 3 pins, because if it's got a metal casing and that metal casing becomes live, then it could electrocute somebody if one of the wires gets loose and touches the outside of the casing. Okay, so the job of a fuse is that it melts if the current gets too high. So therefore they have ratings in terms of amps. So you might get a 3 amp fuse, maybe a 5 amp fuse, 13 amps. They are the most common. You could be asked to choose an appropriate fuse to put into something. And basically the fuse rating needs to be higher than the normal current, but not too high. So if the normal current was 4 amps, you would need to put in a 5 amp fuse, because a 3 amp fuse would blow all the time and you'd need to replace it because the normal current is too high for a 3 amp fuse. If you had a 4 amp fuse and you put a 4 amp like appliance and you just put a 13 amp fuse in it, then the current would get much too high before the fuse melted, which means that the appliance could set on fire, creating many more problems. So it needs to be an appropriate value for the fuse that is appropriate to the appliance. So I suppose in the context of a question, you could be asked to calculate the current going through something if you were given other values, so the power and the potential difference, or being told it's on mains, and then to choose an appropriate fuse for that. So moving on to power then. So if we recall from P1, power is the rate of energy transfer. And rate being over time per second. So our equation that you need to learn is power is equal to energy over time. We also know from P4 that power is also equal to current times potential difference. And we could combine these together. So if we rearrange the power equation, we would have energy is equal to power times time. If we substitute in this P for what power equals in terms of an electric circuit, what we can work out is that energy is equal to current times potential difference, because that's the same as power times time. Now, this isn't on the equation like sheet. It's not something that they necessarily tell you that you have to learn, but on the higher paper especially, they might ask you a question where you have to work out the energy of something and you're given the current, potential difference, and the time. Now, you might get to that yourself by doing multiple steps, but I've had students in the past who found it much easier to learn this equation in addition to the other ones that they've got, because it's easier to recall and use straight away rather than trying to remember the individual steps of how to get there. Now, let's just go on from power for a second. So you might be asked about the power dissipated in something. So often this is to do with, if you've got a resistor or a heater or something in a circuit, it might ask you about the power that's been dissipated by the heater. So remembering from P1 that dissipation is energy being transferred to the surroundings. So if it asks you about power dissipated, the equation that you use is P equals I squared R. So you don't need to know where this comes from necessarily, but for those of you who are interested, if you consider that we have P equals IV and V equals IR, so we have this from the last topic that we did as well. If we replace this V with what this V equals, so we would have P is equal to IR instead of P equals IV, which is P equals I squared R. So for those of you who like to know where your equations come from, then that's the derivation for this. So this is basically an equation without using the potential difference, so you could be expected to use this. The key thing with this is remembering that it's I squared, so if you're asked to find I using the P and the R, you need to remember to square root it, because otherwise you're going to give a value that's I squared. So just make sure that you're following all the steps through. Use your calculation technique of writing down your equation, substituting in your values, and then rearranging. There is also an equation without I, which is P equals V squared over R, and we can get to that in the same sort of way by making I the subject here, so you'd have V over R, so you'd end up substituting that into here, so you'd have V over R times V, which is V squared over R. Don't worry about that derivation bit, but it's these equations, and actually it's this one most commonly that you would be asked about. So 2 more equations, both of which are not new, but one is a complete recap and one is done in a slightly different way in this topic. So you could also be asked about efficiency, and the equation that you will have learnt in P1 would have been that it's the useful output over the total input, and then you could times by 100 if you want it as a percentage. Okay, and then remember that it could be energy or power. Okay, so it could be the useful output energy over the total input energy, or the useful power output power over the total input power. As long as it's consistent with what you've got on the top and what you've got on the bottom, that's absolutely fine. And then as the last bit, I just want you to think about energy is equal to power times time. So this is an equation that you came across in P1. You see it in both this and this. So when they say you've got to learn 23 equations, these actually count as 2 of the equations. So and it's the same equation but just rearranged. So yeah, it's still a lot of remembering, don't get me wrong, but it is the same equation but just done in two slightly different formats. So normally energy is measured in joules, and to measure energy in joules we would do power in watts and we would do time in seconds, but the joule is very small for the purposes of measuring the electricity that we would have in the home. So in order to kind of have a better way of charging for electricity, we have a different unit. So if we measure power in kilowatts and we measure time in hours, then if you think about algebraically, we just stick these things together, wouldn't we? So therefore our unit is the kilowatt hour. The important thing with this unit is that you know it is a unit of energy. Sometimes people get confused with the kilowatt bit and think it's a measurement of power, but it's a measurement of energy, the kilowatt hour. And the other thing is you need to be really careful whether you're using lowercase or capital letters here, because it's a lowercase k, uppercase W, lowercase h. And you need to make sure that that is done correctly, because if you aren't really clear about that, or if you give like a capital H, you don't get the marks for it. They are quite strict about that. So this is the kilowatt hour, and it is used for charging for energy. And so 1 kilowatt hour is 1 unit of energy. So and then they charge you per unit, so it might be, I don't know, 16.5 pence per unit, and by 1 unit what they mean is 1 kilowatt hour.